We will continue the discussion on the shape of a static meniscus. In the previous lecture, we had actually determined the shape of the meniscus by first deriving an equation for the meniscus by using the uh, balance between hydrostatic pressure and capillary pressure. And the equation involved a nonlinear equation from the curvature, and we had integrated this equation directly as well as a linear approximation of that equation. And using that, we also determined the height to which the fluid rises, which is indicated as h0 in the figure. Now, what we want to do in this lecture is to take a very different approach to arriving at the same result. And I'll introduce you to a very powerful technique used in calculus of variations. I'll first give a motivation for studying a problem in calculus of variations by first looking at the problem of energy minimization and why do we have to deal with energy minimization. And then I'll introduce you to a few standard examples in calculus of variations, and then we will derive the so-called Euler-Lagrange equations. That's the roadmap for the next set of lectures. So what you see in the figure is a meniscus which has risen to a height of h0, and it's making an angle of theta e at the wall. I have also indicated new surface energies. So gamma SL is basically denotes the surface energy corresponding to the surface tension between the solid and the liquid, and gamma SG is the surface tension between the solid and the gas. And gamma is our usual surface tension between the liquid and the gas. Now, why do we have to deal with the extra surface energies? Because in reality, when basically if you did not have any plate that is dipped into the bath, then the interface would be perfectly horizontal, and there is only one surface energy, that is, or only one surface tension, which is gamma. But the moment we introduce a solid plate into the bath, if we dip a plate into the bath, we immediately see that there is a meniscus that is formed at an angle theta e. And this angle that the interface forms at the wall, you expect it to be dependent on the interaction between the solid, the liquid, and the gas. So in other words, thermodynamics will play a role in determining this angle. This is of course in the static situation, and we will have to therefore deal with thermodynamic quantities such as surface gamma SL and gamma SG. Now we'll first take a look at the free energy of the meniscus. And this free energy of the meniscus is primarily the change in the energy from the original state. So original state is where we did not have a liquid bath. So let me make a rough sketch of that. So if we do not have a liquid bath, then the fluid would basically just be in a horizontal configuration, and this configuration is without a plate. It's just a solid, it's just a flat interface. Now we want to find out, by dipping a plate into the liquid bath, what is the change in energy that has occurred. The change in energy, or the free energy of the meniscus, would now be surface energy plus gravitational potential energy, and the changes to the energy at the wall. So what are the changes? If you look at the coordinate system, so we have the origin 0, 0. That origin is chosen to lie on the original flat interface without the meniscus. But now because of the presence of the plate, the fluid has risen to a height of h naught. The part of the solid, what is now inside the liquid, was previously the um, was previously exposed to the gas. So in other words, this quantity that we have now got is the change now involves what was earlier was gamma Sg, that has basically decreased, and in its place what has come in is gamma solid liquid, and it has come in to a height of h naught. Okay, now all these energies that we are going to write down, this energy here, this is energy per unit depth, because we are considering a 2D problem. We're considering a 2D meniscus. So all the energy quantities are energy per unit depth. So what is the surface energy first? So to determine the surface energy, what we will do is we'll choose a different coordinate. Let's say I have a small part, I take a small part of the interface, which I'll call it as ds, and I have another coordinate variable, which is the arc length variable L. So L at this point where the interface, where the contact at the contact line, L is equal to 0, and as L increases, I am going from the solid to the flat interface region. Okay, so the surface energy. Let's start with the surface energy. That is ES, and this will simply be surface tension times the area. Area is just ds into 1, 0 to L is equal to 0 to some arbitrary length L. So I'm basically at some arbitrary length along the meniscus. It's some arbitrary length L that I'm going along the meniscus. If I want the full meniscus, I would just basically go from 0 to infinity. Okay. Now, this quantity, we have this. Now we need the gravitational potential energy. I'll simply call it the potential energy. This is because of gravity. And this quantity, we'll call it as Eg. And what is this Eg? Let us say the horizontal extent is some B. That's the horizontal extent of the meniscus. So I'm going from 0 to B in the horizontal, and in the vertical I'm going from 0 to h, rho times dx dy times g of y. So what exactly are we doing is we're taking a small element at a distance of y, and the area, the volume of that mass is nothing but density times gx dx dy into unit depth 1. Now we have mass, and the potential energy would be mass times gravity times the height, and I have to scan the entire region above y equal to 0, above the dashed horizontal line. So I go from 0 to h and 0 to b. Okay, and so if I do, now we can basically obtain this as follows. So I have 0 to b times, I can integrate in y. So I have rho g y dy essentially becomes h square by 2 dx. This is what I have now. And finally we have the total energy would simply be 0 to L gamma ds plus 0 to b rho g h square over 2 dx plus gamma sl minus gamma sg times h naught. H naught is the height to which the fluid has risen at x equal to 0. Okay, so this is what we have now. Now let's make one more simplification. So if I'm at any arbitrary point on the meniscus, let's say the angle is theta. Okay, so let me make a slightly different sketch on the side. So if this is my meniscus, if the angle is theta, then I immediately know that this quantity will be minus delta h and this will be plus delta x if I go from across these 2 points on the meniscus, and whereas this is ds. I'm drawing it like a small triangle there, but eventually in the limit of delta s or delta x going to 0, we can convert this into differential elements. So now we have sine theta would be dx by ds, cos theta would be minus dh by ds, and therefore I have tan theta would be minus dx by dh, and therefore dh by dx is equal to minus 1 by tan theta or minus cot theta. This is something that we've already seen. We can also write ds as dx by sine theta, or this is nothing but dx times cosecant theta, or that is nothing but 1 plus cot square theta, because that is cosecant theta, and this is dx times 1 plus hx square, right? So therefore we have ds in terms of this. So this can straight away, I can use this ds into the expression for the surface energy, and so now the integration, instead of going from 0 to L, will go from 0 to E. Therefore I now have E will be 0 to B gamma 1 plus hx square whole power half dx plus 0 to B rho g, or rho is rho naught g h square by 2 dx. So rho is always rho naught for us. Even if I do write rho in these problems, please assume that it is rho naught. That's the density, constant density. So this is what we have, plus we have the energy terms, the surface energy terms, gamma SL minus gamma SG times H naught, right? So we can now combine this into one single integral, 0 to B gamma of 1 plus hx square whole power half plus half rho g h square dx plus gamma SL minus gamma SG of H naught. Okay. Now if you notice here, this quantity, the integrand here, this is of the form f of h comma hx. Okay. Now this quantity is special because the energy E depends on the shape of the meniscus, that is the function h of x. It depends on this function h of x. So what we are really doing is we have an energy, a quantity called an energy, which itself is a function of another function, right? So in other words, E is a function of another function, and therefore E is referred to as a functional. This is a new term in our vocabulary. So basically E is operating on capital F, okay, where capital F is a function of h and hx. So this quantity E is not a simple function, it's a function of a function, and we call it as a functional. And what is difference between a functional and a function? So very simply put, typically if I were to difference between a function and a functional. So think about a function as a quantity where if you consider a function, the definition very broadly, if I give a real number, let's say a real valued function f of x, and f of x is a real valued function, what's the output of this function? The output function of this function will be another real number. So I give an input as a real number, the output will be a real number. Let's consider an example. Let's say if I take f of x is 3x square plus 2. So if x is equal to 2, if I input this into the function, this quantity is a real number. If I input this into the function f of x, then what's the output I get? The output that I get is 3x square, that is 3 times 4, that's 12, plus 2, that's 14, which is another real number. Okay. So that's what a function does. It takes an input and gives us an output, which is also a real number. A functional, on the other hand, is slightly different. What does a functional do? It takes a function f of x, and then if I give it to the functional, let's say I call the functional as j, that could be E in our problem. So we typically represent this functional with using a square bracket, meaning j is operating on f of x, and then it gives me a real quantity. So functions would require something like a real quantity as an input, real number as an input, if it's a real valued function. But for a functional, we give the input itself is a function. So what we now see is that this energy is actually a functional because it itself is operating on another function, which is h of x. Now what we want to do is to look at this functional That's the energy. And let's basically put this in a box because this is an important result. Let's look at this energy. And then what we want to do is we want to minimize this energy. So nature chooses a configuration which minimizes the total energy of the system. What does this mean for us? What it means is what the aim of the goal, or the goal of our study, can be put as follows. The goal is to find the shape of the meniscus, that is the function h of x which will minimize the energy functional E. Okay. And for this, we need to understand a little bit of calculus of variations. I'll give a motivation for why we need to use calculus of variations, and then we will, the basic framework for using the calculus of variations, that is the Euler-Lagrange equations, I'll derive it in the next lecture. But let me first give you the motivation for why we need to look at something like the calculus of variations. Now let's basically consider a function. So if I were to consider an arbitrary function, then if I ask what is minimization of a function? Minimization of a function. What does it mean? What it means is, if I were to graphically represent a function, so let's say this is x and y, I have an arbitrary function as follows. Minimization would involve finding out a point like this. Let's say the question that we want to ask is, minimize this function, find the minima of this function between the intervals x1 to x2. Now this is a well-posed problem, and to do this, what we will have to find out is, if this function is given by y equals f of x, we know that at the minima the slope is 0. So we are going to find out this location f of x such that f prime of x, let's say this point, let's call it as x0, f prime of x at x is equal to x0 is 0. Okay, so how would we do this? We basically look for variations about this point, and if the variations about this point result in a slope of the function to be 0, at that location of the slope of the function is 0, which means that the variations go to 0, then we know that we are at a minima. And of course, I'm glossing over the fact that to be sure that this is a minima, we also need to evaluate the second derivative. But I hope you get the picture that whenever we have an extreme null point, then we have the slope going to 0. But what does minimization of a functional mean? Functional E. What does it mean? So let's consider the same problem that we have, which is the meniscus. And let us say this is my coordinate system. We have x here and y here. I know that the meniscus, let's say I prescribe that the meniscus will basically start at this location, that is at h0. Okay. Now, what I want to do is, I want to find out what is the shape of this function the shape of this function, which will give me the lowest value of energy E. Now, this problem is a bit much more trickier than the previous problem of minimization of a function. The reason for this is because what we want to do is we want to perturb this, or we want to find out all the possible shapes. We want to do one thing, which is to evaluate the shape of this function for all possible curves, all possible values of h of x, and the goal is to find out, is there a special h of x which will give me the lowest possible energy. For this, we need to use calculus of variations, where what we will be doing is we will take this meniscus, let's say the true meniscus, the meniscus that we really want, which actually minimizes the function. Let's call it as h of x. So what we want to do is we want to take any arbitrary meniscus. Let's call this as h bar of x. We will say it is h of x plus a perturbation to this function. The perturbation to this function, or the deviations from this function. The deviations would be, let's say we call it as epsilon times eta of x. So for an arbitrary eta, we want to find out what is the energy what is the value of this functional for this h bar. So in other words, we want to find out h of x is the extremal of E, meaning it will give us the lowest possible value of E. We know one thing, that we want to find out E to find E as epsilon goes to 0, right? And for those of you for whom this topic of functional or calculus of variations is new, it may be a little challenging at this point, but in the next lecture, I'll give a better motivation with other problems in simple mechanics and some problems in geometry to motivate how we are going to study these problems of extremization. And then we will develop the framework for this minimization problem by deriving the classical Euler-Lagrange equations. So I'll see you in the next class. Thank you.